Okay, yeah, welcome again. Sorry, it's me again. I try to keep you awake after the lunch break, so I'm going to talk a bit about the TTC and whether and how we can use that for mixture risk assessment and where the problems are or what the consequences are when we are making the step from individual chemicals to mixtures. Yeah, starting with preaching to the choir, we know that by now what the threshold of toxicological concern is, so I'm not going into details there. I think everybody is going to use that slide here, so I don't make an exception there. So this is the basis here. We know that the TTC is the lower 5% percentile of a pool of log normally distributed nodes divided by an assessment factor of 100. So that's the definition that I'm going to use. We can always discuss the assessment factors, the percentile, etc. But I'm taking that as a given, as the start of my argumentation, and try to take that for the mixtures and take a look at the consequences there. And the first thing is, of course, this 5% percentile implies that we have a 5% risk that any one given compound has a TTC, or that the TTC is not protective enough. So 5% identifies the risk of misclassification, the underestimation of a risk. We can discuss whether that is a sufficient level of protection or whether it's not. But the interesting thing is, if we take a look at what does that imply if we are taking a look at several compounds that are there at the same time, which I guess we all agree is the realistic exposure situation. And it's quite obvious that if you have more compounds, you have a higher risk of misclassification because you have a 5% risk for any one given compound. Mathematically speaking, that's pretty simple to calculate, the overall risk of misclassification. So the overall risk that you have at least one compound in your mixture where the TTC is not sufficiently protective. So that's the mathematical formula for that. That's always a bit hard to translate that into something visual. So here is the plot of that function here. So here you have the number of compounds in a given mixture. And here you have the probability that you have at least one compound in your mixture where the TTC is insufficient, it's not sufficiently protective. And what you see is, of course, the more compounds you have, the higher the risk of a misclassification is. And if you, for example, look at a 14-compound mixture, so a mixture with only 14 unknown compounds, the way you would apply the TTC to, what you see is that for a 14-compound mixture, you already have a 50% chance of having at least one compound in your mixture where you are underestimating the toxicity under the assumption that you have a 5% risk per compound. So in a 14-compound mixture, there is a 50% risk that at least one misclassified compound is present in your mixture. And you can do that for any number of n. If you go up to a 50-compound mixture, remember that we're talking about a pool of a couple of thousand compounds as the totality of the chemicals. We are almost certain that at least one or more compounds are misclassified by the TTC. So this is really, yeah, I think it's a problem that we have an increasing risk of misclassification. We can actually flip that around and take a look at what percentile do we actually need in order to stay with the 5% risk of misclassification. If we say that this is what we agreed upon, that's an acceptable risk because no method is perfect. So what percentile do we actually need to apply in a mixture context? So it again, of course, depends on the number of compounds, mathematically speaking, in equally similar or equal simpler formula there, which we also can plot graphically, and it looks like this. We have a one-compound mixture, which is one compound, where we have a 5% misclassification, or that's what we accept. And the more compound we have in the mixture, the lower percentile is the lower percentile is that we have to use. So the more compounds, the lower the percentile per compound, so that we end up with a total misclassification risk of 5%. For example, a 20-compound mixture, we would need to go down to the 0.26% percentile, which is something that we can't really calculate from the number and the amount of given data that we have. But this is what we would need to do there in order to ensure a 5% overall risk of misclassification. So that was the example of the 20-compound mixture. And you can see the more compounds you have in the mixture, 10, 20, 30, 40, 50, the lower the percentile is that you need to apply in order to end up with 50%. And the interesting thing is, just as a rule of thumb, that's pretty easy to calculate. You see, if we have 10 compound we are going from 5% to 0.5%. If we have a 50 compound mixture, we go to 0.1%. So you have to simply divide the percentile by the number of compounds in your mixture, then you end up again with the overall risk of misclassification of 5%. So that's what you need to do in order to account for several compounds being there at the same time when you are going for the 5% percentile. We know that's just a sidestep away from the TTC. Mixtures are of specific concern for various reasons. One of the reasons is simply that if you have small negligible effects of the individual compounds, several of them, if you mix them together, if you test them, you end up with a mixture effect that is substantially higher than each of the individual effects of that mixture. That pattern is actually extremely stable, extremely strong. You find that completely independent on the endpoint, on the animal, on whether you go for bacteria or whether you go for rats. It doesn't really matter. This is a pattern that is extremely strong and really independent of the endpoint exposure situation, etc. So the thing is, what we have is small negligible effects might, under certain circumstances, add up to a substantial non-negligible effect of the mixture. That's why we are concerned about the simultaneous presence of several compounds at the same time. We have possibilities to actually connect the observation to a predicted mixture toxicity. We have two models that are defining the cornerstones of mixture toxicology. I'm going a bit more into details there in a second, but it's still the same thing. The small effects here might add up to a substantial mixture effect. So just to summarize that, the thing is, mixture toxicity is higher than the toxicity of each component at the concentration present in the mixture. That's the typical case that we are facing. And the other one is, the conclusion from that is that compliance with individual threshold values does not necessarily safeguard against unwanted mixture effects. We have cases where that really it's obvious it doesn't safeguard. We have others where the jury is still out, so it does not necessarily safeguard against mixture effects. Okay, what does that mean for the TTC? And the good thing is that's the scientific opinion on mixture toxicity assessment that has been published in 2012. I think it was from the 3 scientific committees of the European Commission, SHARE, Senior, and SCSS. And there they are actually using the TTC as one part in order to guide people through a decision tree for how to do a mixture assessment. So if we just zoom in on that part here that concerns the TTC, we need information on the mixture composition, and if that is the case, if it's not the case, then you have to follow another line of reasoning. But if that is the case, if we know how many compounds and the chemical nature of the compounds, then the critical question is that one here: is the exposure to single components and to the combined exposure of the components with a similar mode of action larger than the TTC? And then you continue to work from there. And then the next question here is information on mode of action for each component available? And if the exposure here is actually, if the exposure to a compound with a similar mode of action is not larger than the TTC, then you go back here and you don't have to do anything. So the idea behind that here is that only compounds with a similar mode of action count. The others don't count, they don't add to the mixture effect. And that, of course, is, first of all, what you see is it's logically a bit of a problem, because you take the decision on the similar mode of action here, and only here you are asked whether information on the mode of action is available in the first place. That logic, it has to be flipped around. It has to work the other way around. Otherwise, you will never say that I don't have any information available. You would never end in that pathway here. But the reasoning behind that is that compounds with a dissimilar mode of action do not contribute to the mixture toxicity below their individual TTC. So that's the reasoning behind that scheme there. Or the other way around, if the exposure to the compounds with dissimilar modes of action is below their individual TTC, there is no mixture risk below the TTC. And if we accept the TTC as a sound threshold value, then we don't need to be concerned about potential mixture effects. So if they are dissimilarly acting, you're safe. let's see what's the reasoning, the rationale, the concept behind that. And it boils down to those two old, well-known concepts for mixture toxicity: concentration or dose addition, and independent action or response addition. So that's the names of those concepts. This one here is supposed to describe the combined action of similarly acting substances, and that's the one for dissimilarly acting substances. So just bear with me for a second. I'm not going into the details of the mathematics here, but that one here is the critical one when we're looking at compounds that don't share the same mode of action. And the idea behind that, here is the formula for an n-compound mixture. Just to make it more simple, this is the formula for a two-compound mixture. So what you're doing is you take the individual effects here and you more or less add them up to the mixture effect. And that means as you're working with effects, as soon as the effects of the individual compounds are zero, then you can do whatever you like. You will still end up with a mixture effect of zero, which is really great because that means we don't need to be concerned about any mixture effects. And that is the rationale behind that. You don't have a mixture effect. Paul Price concluded that in a publication in 2009. If that is the case, then the TTC for the mixture is simple, the smallest TTC of the individual compounds. So just take a look at the most risky compound, and you sit on that compound and you ignore the rest of the compounds, which makes life really easy, and that's really tempting. But I'm struggling to get the idea behind that if we take a closer look at that. The thing is, that only works if the TTC really actually describes a true zero effect concentration. It only works then. It only works if this condition here really holds true, if we can prove that there is no effect. We know that nulls certainly don't fulfill that criterion. We know that's the result of an experiment, so there's an uncertainty there, there is a minimum significant difference there, there's statistical power considerations there, etc. So we know that. The question is, how about the lower 5% percentile of a log normally distributed collection of nulls divided by an assessment factor of 100? I have no idea whether that's a true no effect level or not. And I don't think that anybody can really answer that question. So that is really an unknown there. So it's really problematic to actually use that as in your line of reasoning there. The other thing is, of course, if we look at from a first principle, what would we be expecting to be a true zero effect concentration? And then we just go back to basic pharmacology, to very basic toxicology. What does the basic pharmacology tell us? And then we come across, for example, the Michaelis-Menten kinetics. Very basic textbook knowledge, undergraduate student level. And we see here that we have a concentration and we have a rate constant here, which we could, as first approximation, say that this is the effect that we're interested in. That's an effect on a molecular level. Some interaction between a receptor and a molecule is happening there. And if we see the only concentration where we don't have an effect, a really true no effect, is if we have a concentration of zero. This is what the Michaelis-Menten kinetics simply tells us. That, of course, doesn't imply that any molecular interaction translates into anything that we can see or that is toxicologically relevant. Of course not. But that's not the question here, because we are looking at a situation where we might have several compounds triggering that system in different ways, but they are still triggering the same system because they are in one human body. So that's a bit of a critical thing there. So the TTC must actually describe a true no-zero effect concentration. We really don't know whether that's the case or not. And only then independent action is really safeguarding us against mixture effects. The other thing is, of course, the compounds really must be independently acting. The compounds really must not share anything. They don't have to have anything in common. They must be completely independently acting. Now we need to take one step back and see what the hell is independent action and where does it come from. Independent action was developed by Bliss in 1939. That guy was happily killing flies in Russia in 1939. Don't get me wrong, there's nothing wrong with killing flies in Russia. Perfectly okay, everybody has a hobby. But the thing is that perhaps we have developed things a bit beyond that. So this is where independent action comes from. The conceptual idea behind that is that each compound is one dice that you throw, and the total number of dice those are contributing but completely independent of each other. So this is the conceptual idea of independent action. And this is what we know about human pharmacology. It might be slightly more complex than that. So I really think we can't really, I mean, the catchphrase here is don't eat the menu. Independent action is a very coarse simplification of reality, nothing more than that. We really have to be careful there. There's another problem here. Let's say we really try to make the compounds as independent as possible, which requires a lot of toxicological knowledge that we usually don't have, especially in a TTC context. But let's say we have two compounds here symbolized by those two crosses here that are as independent as possible. Okay, that's a two-compound mixture. That's the most simple mixture that you can think of. It's definitely not a realistic mixture. So we add another compound, and we add another independent compound, and we add another one. You see what's happening? They are getting closer to each other because we just have a finite space here. If we have just a very high number of compounds, we are filling that space. They are inherently becoming more similar to each other. So again, another violation of the conceptual assumptions of independent action. So again, something you can't really simply take that a priori and use that in the TTC context without really going back to the conceptual basis of that concept. So there are a lot of problems here when you ask for a similar mode of action in a TTC context because you don't have the knowledge there, because you're basing that on the independent action assumption, which you can't prove, where you don't have the data for. So that is really, really problematic to do it that way. The interesting thing is that concentration addition, the evil twin, so to speak, to independent action, makes life much, much easier. I'm not going into the mathematical details here, but if you want to ensure that the effect of your mixture is not higher than the effect of the TTC, which is what we want, assuming that we agree that that TTC is protective, we don't want the mixture effect to be higher, then what you have to do is you take the TTC and you divide it by the number of compounds. So again, the critical measure that we need is the number of compounds that we are expecting or that we see, the number of peaks in a GCMS chromatogram or something like that. That is what we aim for, and we have to adjust the TTC with that value in order to reach the same protection level as we would reach for each individual TTC. So if we take all these things together, what I would like to do is I would like to really suggest a slightly different flow of argumentation, how we use the TTC in a mixture concept, in a mixture context. The first question that you always need to ask is, are there any significant interactions that are likely because of the chemical structure, because you know that from similar compounds and things like that. So if you have interactions with, I don't know, cytochrome P450s or something like that, then you have to really do a detailed case-by-case analysis. You can't put that in a general scheme. If you don't expect that, or if there are no indications for that, you continue. And the first check is, are all the concentrations in your mixture at a concentration TTC, their individual TTC divided by the number of compounds? If that is the case, no worries, the mixture definitely won't be more hazardous, more risky than the TTC. So there is no reason for concern. You're done. We can do something better with our time. Things are okay. If that is not the case, then you can't avoid actually calculating things according to concentration addition and see whether the concentration of the mixture is above or below the TTC of the mixture. And if that is the case, if the mixture concentration is lower than what you predict by a concentration addition, again, no reason of concern, no worries, continue with something else. If that, again, you can't prove that, then you can start thinking about whether independent action is a way out, whether independent action would actually help you to get a better understanding of what's going on. But for that, you would need a proof of a dissimilar mode of action, which you usually won't be able to get because you simply don't have the data for doing that. So if you have proof of dissimilar mode of action, then you can do a more detailed mixture toxicity analysis. You can consider independent action here. I'm not going into details there. And if you can't prove that, then you have to do the risk assessment, risk management based on concentration addition. That is, in terms of what we know about the performance of the concepts, in terms of what we know about the input data and the basic assumptions of the concept, a more stringent or more logical flow on how to account for mixture effects or how to assess mixture effects. Okay, that leads me to summary and conclusions. The first thing that, the first part, so to speak, was we have to be aware, or we have to think about that the use of the lower 5% percentile leads to an inflated misclassification risk of mixture. Misclassification risk defined as the risk that at least one of the compounds is not captured by the TTC. So the more compounds you have there, the higher the risk of a misclassification is there. In order to keep the misclassification risk at 5%, the percentile needs to be adjusted accordingly, according to that mathematical formula, rule of thumb divided by n. The mode of action-driven mixture assessment is something that people are struggling with even in situations where you have a lot of toxicological data, where you know a lot about the compounds, and still it's really the question, what is different modes of action, how dissimilar is dissimilar, and things like that, and we can start discussing adverse outcome pathways and whatever. That's nice tools, but usually it's demanding, it's data demanding, and it's something that we don't have in a TTC context. That's not what the TTC is applied to. Independent action is of very, very limited use. I would be happy to realize that I'm wrong here, but I don't think that there is any real animal, human toxicologically oriented study out there that shows that independent action actually works for a multi-component mixture. So it's an unproven concept in the human toxicological context. The application of independent action does not allow the conclusion that mixture effects are absent at low doses. They can be absent, but you can't say it's independent, there is no mixture effect. That doesn't work. It can be absent, but it also can be present. That depends on the specific situation. I would suggest we simply start by using concentration addition for estimating the mixture TTC, and we do that by simply dividing the individual TTCs by n, by the number of compounds. And that is one of the major challenges to get a good definition of that n. What's the typical n? What's the n for a specific exposure situation? If we don't do that, we are running into severe problems. I think if we do that, we can incorporate that into a tiered approach. If we don't do that, if we do that mode of action based, and if we try to use independent action at a very early stage, although we don't really know whether the concept applies or whether it doesn't apply, and what the error margin is that we are accepting there, I think what we're ending up with is a structure that ends up looking something like this. So we are really building assumptions on assumption on assumptions. They are all shaky. They all have an error probability, or sometimes even almost a certainty. So the whole structure becomes a bit shaky, I would say. So I think we need to get away from that. And with that, I would like to conclude, and thanks for your attention.